Welcome to this week's Crunch seminar. And today we again have two speakers. And the first speaker will be Professor Ulisses Braga-Neto from the Texas A&M University. So Professor Ulisses Braga-Neto is a Brazilian-American electrical engineer. He received his PhD in electrical and computer engineering from the Johns Hopkins University in 2002. And then he joined the Department of Electrical and Computer Engineering and at Texas A&M University as a professor in 2007. He received his NSF Career Award in 2009 and the Outstanding Professor Award from the Department of Electrical and Computer Engineering in Texas A&M University in 2013. And currently he is the director of the Scientific Machine Learning Lab at the university. And his research focuses on the statistical signal processing and machine learning with some applications in bioinformatics and other scientific areas. So let's welcome Professor Braga-Neto for his presentation with title Self-Adaptive Physically Informed Neural Networks. Yeah.
Thank you very much, Henry, for your very nice introduction. And so I'll be presenting here actually preliminary results. I like to think about this as a work in progress. We obviously have already presented it at this recent spring symposium on scientific machine learning of the AAAI conference society. But this is still a work in progress. And so I'd like to share with you some of these results. I'd like to take a couple of minutes, I mean, if you excuse me, to talk a little bit about our scientific machine learning lab. So, this is a new effort that we are doing here, and it started in January. We have faculty from several different departments, from engineering and science, and, mathematics. So we have a couple of postdocs being hired. They're going to start now in the summer. There is support for graduate students, community events, etc. So please take some time, if you can, to visit our website to learn more, a little more about this. These are some of the people I promised them I would show them here. So we have Jian Tao assisting us, Lisa from HPC, Li Fan, professor of astronomy, Raimundo is in the materials area, Raktin is in aerospace, Yalchin is a mathematician, Eduardo Gilding is petroleum engineering, and then we have Levi. So far, the project has focused on, the lab has focused on three areas: microstructure informatics in materials, reservoir simulation. I'm going to have one example from this later in the talk. So reservoir simulation and supernovae, so modeling the explosion physics, etc. So we hold events at the lab. You may see some familiar faces here. I'm sure you know at least Paris. And we have been we've been holding seminars and hackathons and mini courses. And so we plan to continue to do that. Okay, so now let's start my talk. So I'm actually, I'm an electrical engineer, and I'm a statistical signal processing person. I worked in image processing for a long time at Johns Hopkins and elsewhere, and then in machine learning, statistical learning. So that's my main area of interest. So for me, scientific machine learning is machine learning. Okay, so that's the perspective I want to bring to this, which reflects my background. So I see scientific machine learning as still involving an input, which is data, and an output, which is a target property that you're trying to predict. And you have a forward modeling direction. I don't know if you can see my pointer, probably not. But I have a forward modeling direction, and I have an inverse modeling, of course, direction. And in the middle, you have this machine learning module, but now it's complemented by physical laws. And so I'm interested in statistical questions. For instance, how much data do you need? Are these prediction algorithms consistent? Are they going to converge as sample size increases, and such, and so on and so forth? But with that said, I'm also very interested in the scientific computing component of this, and I'm learning all the time about this. Okay, so in case you haven't heard, there's this thing called physically informed neural networks. And it's interesting because what you see is that if you look at the output, once again, I don't have my pointer here, but if you look at the output of this neural network, it's an expansion. It's a basis function expansion. But of course, the basis functions are trainable. That's the big difference. So you train them by using initial condition points, boundary points, sensor data, and collocation points. Sensor data, if any, right? You might not even have data. So you make the output of the neural network satisfy the initial boundary values, any sensor data values, and the PDE on the collocation points. So it is a pseudo-spectral method with a trainable basis. So by being a pseudo-spectral method, it's a high-order method, right? So it can be very accurate, but we are still learning how to train this method, right? So, I mean, that's one of the major focus. I've been talking to Paris about this as well. He's also interested in this, as you know, of course. And this talk is in this context of how to train the PIN, okay? All right, so the baseline PIN, as you all know, it consists of an approximation network, what we already discussed, and then there is a residual network. Of course, you have a loss term, which contains several terms. There's a loss for the data, there's a loss for the residual, for the boundary points, and for the initial condition points, of course, in an initial boundary value problem. So in this talk, we'll be mostly concerned about this loss and how we can manipulate this loss in different ways. So here's an example. It's a very successful example, right? Is the viscous-Burgers equation. So the viscous-Burgers equation is a kind of a simplified Navier-Stokes equation, right? In the one-dimensional case, it has been studied ad infinitum, and pins work very well in this particular with this particular parameter setting here. I mean, it's a stiff PDE. It generates shock fronts, but the pin is able to do this very well with just a small number of training iterations, like 200 Adam plus 200 LBFGS. I mean, this is very fast. When you're running this on a GPU, it's a few seconds, and it'd be very hard for a traditional numerical method to beat that, I think. But as we're gonna see later in the talk, you can break it, and we're gonna see it. But with this kind of parameter settings, it is. I mean, it's hard not to converge. I mean, you can change the number of collocation points. You can use very small number of collocation points. You can use, and it still works. Okay, so it's marvelous. With very small L2 error. This L2 error actually is not a very good, it's not representative. You know, you can get smaller. Of course, you only use 200 iterations. Okay, now let's look at a different equation. And that's the one that we have been looking for, mostly because we have been involved in this collaboration with materials in microstructure informatics. And so, so in this kind of phase field modeling equations, these are reaction diffusion PDs with a double L potential, and therefore, you know, the response, the solution is going to decompose into two phases. As from a random initialization, it will spontaneously decompose into two phases. And this is one example of a one-dimensional Allen-Kahn. And we can see here high fidelity, I'm sorry, we can see here, well, maybe not. Okay, we can see here the evolution of this equation. And you can see that it is a very challenging PDE because it generates these very fast transitions. Okay, so what we observe with this kind of PDE is that, well, the baseline pin doesn't work. And we can try, you know, a large number of iterations and collocation points, etc. And it will not converge. Another challenging feature of this particular Allen-Kahn is that you have the free boundary, the periodic boundary condition. So it is, the periodic boundary condition is also very challenging for the pin. So this is what's happening here. I'm sorry, we already saw this. And now the question that we ask is, what happened, right? So what happened, and how can we fix this? So I'm going to go through quickly through a few solutions that have been proposed, and to set the stage and to give you a context. So the simplest one is, let's just weight the different loss terms. So, okay, so the Allen-Kahn is a reaction diffusion equation, okay, and it is time irreversible. So we have to approximate it well early. If you cannot approximate it well early, there's no hope, okay? So let's put a very large fixed weight in front of the initial loss term. And that's what these guys did, okay? So we call this the non-adaptive weighting solution, all right? Another approach that the same people propose in the same paper is this time decomposition approach. So now let's decompose the domain into bands of intervals of time, and let's train the network first initially on the first band close to the next to time 0, and then after we have trained it there, let's expand the domain, and let's add new collocation points, and let's train it again. And then let's continue to do this. So the hope is that you can push forward that information from the initial condition forward. So we call this the time decomposition approach. Another approach, which you probably are familiar with, is the learning rate annealing. So this is proposed by Paris and his students. And here, the motivation for this is where they observed that the residual terms, the gradient of the network weights with respect to the evaluate on the residual terms is much they are much larger than on the initial boundary condition. So in other words, the neural network is not responding to the information on the initial boundary, okay? And so they did this by, they plotted the histograms and you know, they did lots of analysis, theoretical analysis as well. And they found out that this is the case. So the proposal that they did is, okay, let's stick weights in front of the loss terms, not the residual loss. Let's leave it alone. But let's take the boundary and the initial condition losses, and let's take a weight in front of it. And this weight is going to change during training by picking at the distribution of the gradients. So it will, these weights will go up and down according to this imbalance between the gradients, okay, between the gradient distributions. So we call this well, they call it the learning rate annealing approach. An interesting thing to observe is that these weights, they are not trained by backpropagation, right? So they are varying during training, but not by backpropagation, okay? And finally, there's the neural tangent kernel weighting. So again, Paris and his collaborators, they published a very nice paper. And well, they derived the NTK for pins, and they show that it has some of the same theoretical properties that the NTK for standard deep networks has. With random Gaussian initialization of the weights, it converges to a constant kernel at time 0, as in the infinite width limit of the network. It also stays constant during training in the infinite width limit. And they also showed that the training error for the ith data point, it decays at a rate that is controlled by the ith eigenvalue of the NTK. So based on this observation, they proposed another weighting scheme where the weights now are determined by the eigenvalues of the NTK. So in particular, you don't need to calculate the eigenvalues. You can take the trace of this. You can take the trace, because the sum of the eigenvalues of the entire NTK, and you can also take the trace of the boundary condition and initial condition sub-kernel, and you can take the trace of the residual sub-kernel. And therefore, okay, so you don't have to calculate the eigenvalues, luckily. But this means that, okay, so this, because in the actual non-infinite width limit, this kernel is changing during training, these weights will also go up and down during training, right? And they will adjust. So this we call the NTK weighting. This is something we are still investigating, and of course it has some similarities with the annealing scheme. It's kind of similar, even though here you also weight the residual. Okay, so these are some of the proposals that were made to weight these loss functions, and the common thread has been that yes, the residual trains much faster. Okay, the initial boundary conditions are tough to train. This was the message, okay? All right. So here is the idea we had, okay, about, 9 months ago, and we're still working on it. It's a work in progress, but the idea here is to use the philosophy of neural networks, which is to do not mess with the neural network. Let it learn by itself. Do not impose hard constraints on the network. I mean, obviously, that's not true. I mean, this is a general statement, okay? Obviously, there are certain conservation laws and symmetry conditions that could be beneficial to introducing the neural network, and definitely having the correct architecture for the neural network is very important. But the general principle is that, okay, I mean, the neural network can learn by itself, So let's use these weights, but let's let the network learn these weights by backpropagation. And furthermore, we can put one weight for each data point. We don't have to put a single weight in front of the entire loss function. We can put a single weight in front of each data point loss and let the network adjust this weight by backpropagation. Okay, so the new loss function looks like this. And so now you have the network weights, but you also have these adaptive weights. And they all train together end to end, okay? The new loss functions, they have the adaptive weights in front of each data point, like I said, but they also have a mask function, G, which is a non-decreasing function, which allows you to shape the evolution of these weights to a certain extent. Okay, so we'll see some examples. But so that's the idea. I mean, it's a simple idea, but let's see how this actually works. Any questions so far? I mean, if there are any questions.
Ulisses,
Yes.
I mean, I know Paris, he was a student, and all these other people who came to your lab, but you know, we will also be working on this. We're not sitting idle. For example, the XPIN, method that we use is basically a space-time decomposition.
I'm aware of that. Yeah.
So it overrides the one that you showed. What Paris and what you're proposing here, actually, our adaptive activation function does exactly that. In fact, we just released the Kronecker neural network, which is a very general framework where we have rowdy functions. And that you can accomplish the same thing in terms of stiffness and the oscillations, stiffness, which is carried by the weights, by using adaptive activation functions at the layer level, at the neuron level, and so on. But especially the one that we just released, the Kronecker neural network, but it has the flavor that you're talking about. We make them computable. Of course, it's more expensive, but you can solve the problem. So there's a lot of stuff that is also we're not sitting. So I was just thinking of, like, you know, after Rome was built, then the people try to find many ways to go to Rome, and there are many ways to go to Rome.
Absolutely.
But no, that's these are all the issues that you mentioned. There are open issues, but many different ways, including the periodicity boundary conditions. One of my former students, also at Purdue, he wrote a paper in JCP, which I handle on exactly enforcing periodic boundary conditions. So each one of them, you know, and I handle many papers every week on different journals, SciAm journals, Computer Methods, Applied Mechanics, Engineering, and so on, where I'm editor. I handle lots of papers on all the papers on AI, and they're all looking at all these aspects, which is interesting, right? That's why the idea, like you said, so that's how we grow the field. But I just want to make that point that we also have our take on it. It's just that we don't make it as dramatic as Paris, because Paris, you know, he became assistant professor. He wants to say that everything didn't work before him, but that's not exactly true.
No, Paris is a great guy. Here, I mean, look, I completely agree with you. I mean, it's very hard to keep pace. The area is exploding, and this is good, but it can also be bad. It's hard to keep up. This particular paper that you mentioned, I have to read. I'm gonna look for it. So it's recent, right? It's about. Yes,
this is recent. We just released it, actually. The Kronecker Delta, I've been working on it for a while, but they just released it, yeah.
Okay, so I'm going to look for it, definitely. And the XPIN is something that we also are very interested in some collaborations we have with heat transport and non-uniform heat conduction and this kind of thing. So the XPIN is definitely very important for us as well. So, okay, thank you. And all right. So the next question is how do you train this?
Yeah, excuse me.
Yes.
I have a question about the previous slide about this mask function G. So I understand that why G has to be non-negative, why G has to be differentiable, but why does G has to be strictly increasing?
Yeah, that's a terrific question. I'll try to give you an answer for that. Okay, but later I believe that this can be relaxed as well, and we are investigating this. But let me show you. Okay, next, and why it's interesting that it is increasing. Okay, so let me show you. So. So the basic idea here, and that's the key idea, I would say, is that you're looking for a saddle point on the loss surface. So you're looking to minimize the loss with respect to W as before, but you're looking to maximize it with respect to the lambdas. And why? Why is that the case? Well, if you look at the gradient descent step, like here in these 4 equations, then you're going to see that we have a positive sign for the weights, for the self-adaptive weights, right? And the usual negative sign for the network weights. But if you look at the gradient of the loss with respect to the self-adaptive weights, you're going to see that, first of all the gradients are non-negative, because the mask function is strictly increasing, right? And so the sequence of self-adaptation weights itself is monotonically increasing. But not only that, you can see that the gradient is larger when the corresponding loss term or loss terms are larger, okay? So when the loss term for that particular point is larger, the gradient is larger. Okay, so the gradient component for that point is larger. So basically, you're going to penalize more the areas where you're not doing well, and you're going to keep penalizing that. Okay, so it's very unforgiving. Okay. So, you know, the more you do not respond there, the more the weight increases, okay? And so it's the kind of an old-fashioned system. And this is basically the idea, all right? I mean, we would like like I said, the G to be increasing, because we would like these weights to always increase when you're not doing well, okay? But we are also looking at the situation where you might want to let these weights decrease when you start doing well. So you're not frozen in place. Okay, you started responding, then I can decrease that weight. And at this particular time, that's not true. At this particular time, you know, once the weight increases, it can never decrease, okay? So, but yeah, so this is what we have right now.
Dr. Braga-Neto, I'm going to take a stab at that question specifically too, is if you allow the network or the trainable weights to decrease, it's a lot easier to decrease the total loss function by just making that weight very, 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 very small. So whenever it back propagates against it, it says, if I just keep dropping this weight, I can lower the loss function without even training the neural network weights. And
yeah. But, you know, but the actual loss that we're interested in is the unmasked loss, right? It's the unweighted loss.
Exactly. So the unweighted loss, the unmasked loss will actually not decrease very much, because the masked loss decreases substantially. So the total loss function will decrease, but the masked or the unmasked loss, the neural network loss, won't. So you have to make the function, the neural network weights increase where you need to penalize the training. Because that's how you actually cause the neural network weights to say, oh, I have to do this now, instead of the mask weight. So the neural network weight will, the neural network will cause the loss to go down.
It's entirely possible that that's the only possible way to go, right? I mean, we have to check, yeah. But you make a good point. I mean, don't let off, right? I mean, so if,
we are continuing to dig into other ways of training this too.
Yeah, exactly. We are. This is a work in progress. But So here are some examples of masked functions. So the quadratic masked function is the one that we use the most. It has a very good, increasing derivative, and so it works very well. I mean, you can have a cubic masked function, so polynomial masked function in general, but you also could have bounded loss functions. So if you want your of course your weight cannot increase forever. So in practice, all masked functions have to be bounded. But you could have like a logistic shape where the weights increase to a point and then they saturate. And you can make this logistic very sharp so that you almost have like a binary mask of weights. Okay, so either the weight is low or then it jumps to high after a certain point. So you can play with the mask function to achieve different behaviors like this, okay, for the weights. Next, I'm going to show you the results that we got with the Allen-Kahn. So here we have a small network, relatively small network, 4 layers, 128 neurons, and then we do 8,000 Adam plus 8,000 LB, Newton, pseudo-Newton kind of thing. We found out, and not just us, but a lot of people, that the second order does not really work with pins unless you're close to the solution. I mean, otherwise it blows up. So we use the Adam to get close to the solution, and then we use the second order to fine-tune the solution. So here you can see that we were able to get a very accurate solution for the Allen-Kahn. And one thing that you can see, so here we are comparing against the time adaptive, the non-adaptive, and the baseline. Of course, the baseline and the non-adaptive don't really work, but we can be the time adaptive. Remember, the time adaptive is the one that is domain decomposition and you push forward the information. So we can beat that substantially. And here you can see the trained mask. And the trained mask is an interesting picture because you can see where the weights increased. And in fact, the weights are increasing near time zero, as was expected by all the theoretical and empirical evidence, but not uniformly across the spatial domain. They are increasing over or near the fast transitions early. Once you can capture that, you're doing fine. Also, they increase very fast also on the initial boundary. I mean, of course, the initial condition.
Ulisses, how much? This is very interesting result. Which mask are you using here, and how much what's the extra cost for the weight?
Yeah, here is a quadratic mask, and it's a quadratic mask. The additional cost of training these weights is not large. Levi can say a little bit more about this, but I've been running it also, and I almost cannot tell any difference. Is that true, Levi?
Yeah. I'll quantify it here in a couple of seconds, or in a couple of minutes when I.
Yeah, but that's the idea, is that computational is not too much. It's not too expensive at all. And you can see, and this is very consistent. We can run it again and again, and we're going to get a mask very, very consistent.
What is interesting, and you point out the Paris paper, is to look at the balance of the different history terms. I don't know if Levi has that, or if you have a plot of the history losses for the different terms, so we can see how they balance out, because that's basically exactly the imbalance of that is the issue.
Yeah, we don't have that plot, but we do have a plot. We don't have it yet, but we have a plot for the weights themselves and the collocation weights in the bottom right. You can see that the adaptive weights for the initial condition, they jump much faster and they keep growing, with a much larger, steeper slope. And you can see that, okay, so almost immediately from start of training, okay, so this is against the training iteration number, times 100. Almost immediately they jump at the initial boundary with respect to the collocation point. But of course, we also would like to see this curve for different regions of space-time. So I suspect that the collocation points will grow faster, slower, earlier, the left region, than in the right region, which we can see by the train mask, the final train mask, of course. So, so this is an interesting result that we got, and like I said, it's a work in progress. But we are. I mean, like I said, this is a very important PDE for us because of the phase field modeling equations. These are really tough equations, but we have a little more, a few more results. We have results for burgers as well, and you can see here that of course burgers, okay, we can do well with the baseline, but it's good to know that at least we don't hurt it, right? I mean, this doesn't hurt the burger solution. It actually improves it a little bit. As we can see, okay. And we can see here the train mask, and here we can see that more or less the same idea. It's bigger at the beginning. It's concentrated around the shock transition, so it agrees with the previous case. We can see here the residual and the absolute error. Of course, it will be also bigger around the shock.
I think I like a lot the train mask maps that you have, because they give you a lot of insights.
Yes,
so
absolutely.
That's in one look you can tell what's going on. So it's really interesting, and we have some tough problems actually with phase fields and the crack propagation. So that's where it would matter a lot. So I have a couple of postdocs who are working on it. So that's great. This is a great result.
Thank you very much, George. So let's see, there's another one here, which is Helmholtz, and it's the same story. This is also a stiff PDE, as Paris shows in his paper. And you can see that, okay, so it does a good job. And using fewer iterations of training. The train mask, also same story. It's going to be concentrated in the transition regions, yeah. So I mean, essentially, we can get a more accurate result with fewer training iterations, and this is okay. Now I'm going to talk about in this last part of the talk about another phenomenon that we have recently observed. You may be aware of this or not, but this is something that came up in our collaboration with Eduardo Gilding from Petroleum Engineering here and his students, and they contributed this example. So I'd like to acknowledge that. And so this PDE is called the Buckley-Leverett PDE. It's again in this family, of fluid dynamics PDEs, and it's used to predict so you have two-phase flow, water and oil, and in oil production, you want to inject water in one place so that oil comes out in another place, and you want to predict how this wave front behaves between the water and the oil. So I have two immiscible phases, and you're going to push one here on the left, and there's going to create a wave, and this wave will propagate to the right? So S is the water saturation, and F is it's called the fractional flow of water. It depends on the rock formation properties, porosity, etc., and also the fluid properties. But this fractional flow can have different shapes, and the shapes influence the behavior. So if it's a concave shape, then in all cases you're going to have a formation of a shock. But with the concave, it's going to be much more smooth, as you can see on the left here. If you have a convex shape, not concave, but convex, then is the other extreme. You're going to have a very sharp shock is going to form in the water saturation. And you can also have an intermediate behavior. So you have a non-convex shape. And these are the three behaviors that you can see. All right, so if you try to apply the PIN to this PDE, it does not work. Not the baseline, not the self-adaptive, nothing works, okay? And we can see here, but it works for the convex, I'm sorry, it works for the convex fractional flow, but it does not work for the convex or the other one, the intermediate one. For the concave, it works very well, okay? So it works very well. And this is a tough PDE. It's a hyperbolic type PDE with shock formation. Well, it works very well for the, both work, the self-adaptive, the baseline. There is a little, again, we're a little more accurate, not much more, it's like burgers, okay? A little more accurate with fewer iterations of training, but they both work very well, okay? And, but they do not work at all with the convex fractional flow or the other case. Just doesn't work. So what these people from Stanford observed, they also work in petroleum area, is that if you introduce a diffusive term with a small diffusion coefficient, then suddenly it works very well. Okay, and so this is an interesting observation, and we can see here this fact, you know, with a fractional flow, with a convex fractional flow function, with a very sharp shock, the pins don't work. But suddenly, when you add a very small diffusive term, they work very well. Okay. Same thing for the non-convex fractional flow. So you're gonna see this kind of behavior. So okay, I mean, so what's going on here? And you see the convex, the diffusion coefficient can be very small. In this case, it's only 0.0025. Okay.
Ulisses, can I add something here, because this is well known in mathematics, of course, in weak solutions, and Ita Tadmore a long time ago introduced the concept of spectral vanishing viscosity. So for this hyperbolic laws, if you basically, so not constant viscosity, it's a mode-dependent viscosity. It's called spectral vanishing viscosity, which I have used extensively since then in LES, large simulations. But here, for example, what you do by adding diffusion is in fact you impose uniqueness to the problem because you have the correct thermodynamics. In other words, you impose the entropy condition.
Okay.
So if you impose the entropy condition explicitly in the loss function, like other people at Sandia did, and not Trask and others, you can still get that. So it's a way, so this viscosity, or the most, I know Celepi, I was there at Stanford and gave a talk early on pins. It's good, but it's not, it mathematically is not, you know, you just not satisfying. The spectral vanishing viscosity approach, you can actually show that you can recover spectral convergence, even for discontinuous solutions, because you choose the right solution. But essentially what it is, at the end of the day, what it is, it's a thermodynamically consistent framework. You impose the entropy condition indirectly, but also directly would work. Yeah, this is just a parenthesis.
That's the physical, okay, thank you very much. So, I mean, I suspected that you already knew about this, of course, but did you know about this behavior of pins?
No, we do shock, so we see that that's right. They fail unless you do L1 minimization. You have to do the entropy condition and so on. Yeah, that's true. We did supersonic and hypersonic flows. We have a project with DARPA on that.
Okay, thank you. Okay, so that's very interesting. And so I mean, and of course, it's the same case with burgers, right? I mean, so it's the same case. So you can break it if you make the diffusion coefficient too small. You can break it. And of course, because then you're reducing the parabolic nature of the PDE. So Burgers is a competition, right, between the diffusion and the convection. So if you lower the diffusion coefficient, then convection wins, let's say. But the interesting thing is that, you know, the solutions still look very, very unchanged, because this is a small change in the diffusion coefficient. I mean, the solution looks unchanged, but the pins cannot work at all. And you can see here a typical representative results for 10 to the negative 6. So it works with 10 to the negative 2 very well. I mean, cannot make it not work. And suddenly, when it's 10 to the negative 6, you can never make it work. You know, it cannot capture that shock. Now, something interesting that I noticed, and this is just a speculation, but, you know, I noticed that if you reduce the number of collocation points, it actually can capture the shock to a certain extent. Of course, the resolution is smaller, but, you know, you can actually get smaller L2 errors, and you can actually get closer to the shock by reducing the number of collocation points. And I suspect that this has to do with the geometry of the loss surface. I mean, if you have less collocation points, you simplify the loss surface. I mean, that's just my speculation at this point. But the thing is that, so the number of collocation points are not data. They do not behave like data in statistics, right? I mean, more collocation points does not necessarily translate into better accuracy, or even in the average sense. So, yeah, so these are the things that, you know, we are still learning. But okay, so this is what I had to say. You know, we present these results. I mean, I wish this could move faster, but, you know, we are still working on it, and you know, we believe that this is some promising and potential for accelerating and, you know, and facilitating the application of pins. And I actually did not show, I'm saying here that I showed, but I did not show for some reason, I missed that slide, that this training procedure for self-adaptive pins is actually is a penalty-based method. So you have a PD constraint optimization problem, and use a penalty approach, like impose a penalty barrier. And of course, the sequence of weights must be increasing in the penalty method. And here, that's why we want the weights to increase as well. Perhaps you cannot let them decrease, okay? So hopefully there are some lessons to be learned from the penalty methods in optimization that we can apply here as well. But this is in the paper, okay? So if you go to the archived paper, you're gonna see that, okay? So so yeah, so that's what I had to say, and I'd like to give the floor to Levi now. And what's the time? How are you doing? How are you doing with time?
Yeah. We can let Levi give you the talk. Yeah, his talk.
Yeah. Okay. Thank you.
All right. Yes.
Okay, Levi. So go ahead. I'm gonna stop sharing here as soon as I can regain the use of my mouse. Okay. All right.
All right. Appreciate the opportunity to talk here today a little bit about some software that we've been developing here at Texas A&M. We call it TensorDiffEq. It's a large-scale pin solver for multi-GPU implementation of pin solving. So, like Dr. Braga-Neto said, we're affiliated with the Army Research. I've been working with them since 2019, and they've helped out with some hardware to help us be able to develop things that you're going to see here in this slide deck, as well as here in just a second with some very short demonstration. So this is only a couple slides, so I'm just going to burn through this pretty quick, and then we'll get to the code, and then we'll let everybody on their way today. So TensorDiffEq, the motivation for solving it is that most current pin solvers, actual implementations for large-scale use and consumption, if you will, by the community to solve their problems are limited to single GPU. for the most part. Existing software based in TensorFlow is primarily based on TensorFlow 1. There's a lot of incredible things coming out of the TensorFlow team, optimizations in TensorFlow 2 that are just kind of built in and kind of just work, and rolling into the new TensorFlow version allows you to take advantage of some of those things. The interface for a lot of the pen solvers, if you implement something in Moose or implement something in Abacus, there's a pretty intuitive interface to it, and we were kind of shooting to recreate that, where you sort of define your domain, you define your boundary conditions, and then you hit model.fit and go from there. So we kind of wanted to shoot for this plain English approach of defining what your problem is and solving it. And then there's no really fully open source version of a multi-GPU pin solver. There are multi-GPU pin solvers out there being advertised, but currently, got to apply for access and do some other things in order to gain access to them. And so we wanted to roll one out to the community, have the community actively develop on it, use it, try it, break it, fix it, and do the open source development, and really have an opportunity for anybody who wants to get engaged in the development of the software to be able to do so. So our implementation is in TensorFlow 2, multi-GPU implementation of it. Takes advantage of some of the things like XLA optimizations, grappler graph optimizations, and usage of LLVM. If you're going to run on different places, run on different architectures, you go from x86 to ARM or whatever, then you can kind of, it's a very portable platform. So we want to be able to take advantage of some of those things in the future. Ideally, if you need to take this to the edge, you could do that. You could go from your your GPU workstation in your office and go and put it on a Jetson Nano chip and use it out in the field. So we want to be able to take advantage of some of those architectures that TensorFlow is rolling out with their new software, and that we get kind of as a benefit of building this on top of TensorFlow 2. And so just a little bit about the interface, and we're going to see some code here, but it's like I said, we're shooting for a very simple interface with this, where you just define your domain. In this case, we're going to look at the Burger's equation, a very simple hello world style example, if you will. And you would just go through, you define your domain, what that is. It doesn't have to be, it can be a steady state problem. You don't have to have a time variable that works. But one of the novelties about this is that you could just go through and layer-wise add dimensions to it. So if you have a 3-dimensional, 4-dimensional, 6-dimensional problem, you can go through and add all of those dimensions and just kind of append them to a list, if you will, and be able to go through, and the solvers will work with that sort of interface. So in this particular example, you would add your X and T domains. You would generate, in this case, 20,000 colocation points. This is primarily a colocation-based solver. It's, I feel, important, and we're going to have a slide here shortly, but this is primarily a colocation-based pin solver. There is some discovery, inverse modeling, and some data assimilation stuff that's rolled into the package too. But just for this example, that stuff doesn't apply, but it is in the package. So in this case, you are using the colocation solver, so you generate colocation points. You define an initial condition function. This can be any Python function. And it can be a Boolean function. It can be anything that you can define using a Python function in terms of X or Y or Z or X, Y, and Z, any of those things. Define your initial condition, in this case, using this IC function. Define your upper and lower Dirichlet boundary conditions. In this case, we hard code a value. You can do functions as well. It just doesn't apply to this particular example. You make those into a list. So we'll pick out here. You put those into a list. You define your model that you're trying to build in, a very similar syntax to the original paper that came out a few years back. A very similar syntax was kind of what we were shooting for, because it was very intuitive. And so you can use that and define all your gradients and define your PDE, strong form PDE, just like this. Define your layer sizes. In this case, you take advantage of a fully connected network, but because we're building on top of TensorFlow 2.0, you have all of the nuts and bolts of Keras, because it's all rolled into TensorFlow 2. And so, we have on the website, there's a hacks page where you can go in and actually overwrite a fully connected layer or fully connected network with something like that implements batch norm or whatever. So this is just to kind of get you off the ground with a fully connected network. However, since Keras support is built in, because it's built in TensorFlow 2, anything that's applicable in Keras can be trained using this package. The usability of some of those things may or may not be necessary. They may or may not be useful for things, all these different layer types that you have in Keras, but they all can be rolled in and trained. So in this case, you define your colocation solver, you compile it using your layer sizes, the physics of the model, your domain, your boundary conditions, and then you hit model.fit. And it trains from there. And we'll show the interface here in a second. So this is the Burger's equation. Some of the slides that were presented earlier the results came from the package TensorDiffyQ. And then of course we have the self-adaptive solver. rolled into this. So that's something that we'll actually show here in a second of how to use it. It's a pretty simple modification to this code we just saw to roll that in. So currently we support some pretty basic domains, looking to expand that. I know there's a lot of solvers, a lot of suites out there that have some more expansive domain coverage, and we're definitely looking to roll that in. Boundary conditions, as I mentioned, we got the Dirichlet, function Dirichlet, we got periodic, and then some new, a new addition is Neumann boundary conditions. Initial conditions, like I said, you can linear, nonlinear, anything that you can define as a Python function you can use. Single GPU baseline and self-adaptive, and then multi-GPU baseline solvers, so you can solve a large problem domain if you need to, with a lot of co-location points and distributed across 4, 8, 6 GPUs. It currently supports multi-worker GPU distribution, not multi-node. So we're looking more at that, especially now with our HPC at Texas A&M. There's an opportunity to really dig into that, so we're going to be doing that. You can transfer learn using it because it's built in Keras, and on top of Keras, you can just save your model and re-import it and use it for a different thing. If you want to just modify a parameter slightly, you don't have to retrain from scratch. You can just do that. And then any loss function is supported in TensorFlow or Keras, so that can be Atom is primarily, any loss function, yes, so mean squared error, mean absolute error, and then also any optimizers. So if you were wanting to use anything besides Atom, for instance, you could just roll that in and overwrite the solver using your RMS prop, or whatever you were just, if you wanted to try something different, you can do that way. We also have a discovery model, so you can do parameter estimation. That's built in right now. So we have an example in the notebooks. I'm not going to show it today, but of estimating the parameters from Alan Kahn, and then also as well as data assimilation. So if you have a snapshot of data and you want to roll that into your solution, you can do it using the software. And so with that, I'm going to go over briefly, and I have some Jupyter Colab examples that are up. These are up on the GitHub for the code. So you can just go, and if you go into the TensorDiffEq main page on GitHub and there's a notebooks tab, you can go and you can look. So all of these are available there. But we're going to cover just briefly that example. So you'll just pip install it. It's available on pip. So you just pip install and it'll work. It'll install the dependencies. We run on the most recent version of TensorFlow, which is 2.4.1. I think they may have just released 2.5 in the last few days. But this is being developed on nightly. So so it allows for the latest distributions of TensorFlow to be used. So we'll go through and install the dependencies. You import all the requirements. You define your domain as discussed, and then generate your co-location points. In this case, we'll call it 10,000. Define your initial condition function. Make that list I discussed of all the different boundary conditions you're going to roll into, include your initial condition. So put that into a list, define your physics. In this case, it's the Burger's equation that we discussed, layer sizes, and then compile the model, roll the model, and you'll see here. So we're going to train for, in this case, 2,000 Atom iterations and 1,000 of the LBFGS. You can modify whatever those optimizers are. You can turn off one or the other if you're interested in doing so, but we'll just run through this and you can see how quickly it trains here. So in this case, we're training using Atom. This is a single GPU implementation on a K80, a single K80 on Google Colab. So it's on Google servers right now. So this is running on GPU. Colab is a little laggy. So if you run this on a command line, it's a lot more, it doesn't speed up and slow down like this. But you can see here, so 135 iterations per second, trains pretty quick. I'm not going to wait for the LBFGS, but this will be done in this is about a minute for 1,000.
I would like to jump in here and say that for burgers, you only need about 200 of each.
It's true.
Maybe a little more, maybe 400. And,
yeah.
it works very well and it's extremely fast.
Yes, yeah. This trains really quickly. So in this case, we're going to show a comparison to the high fidelity data just to get an L2 error. So we import that.
By the way, Levi, I'm sorry. Please mention that, this is the baseline pin, right?
That's correct. This is the baseline implementation. So
baseline pin, and then there is a flag that you give to the compile code if you want the adaptive one.
I'm going to show that. Yep, just a sec. Absolutely. Okay. So in this case, we'll calculate the L2 error, and we just show. So this is a similar plot to what was in the original paper, also what's in the TensorDiffEq, or I'm sorry, the self-adaptive pin paper. So we can see here that the L2 error on that with 2,000 Atom and 1,000 LBFGS is about 1% approximately L2 error. And so if we take this and implement,
you can get better than that if you have more iterations. Yeah, but
absolutely. In this case, if you want to implement the self-adaptive, so we're going to show just some minor modifications here. The co-location weights you would define, the U weights you would define, you would compile those in. So this is the only modification You just add in the is adaptive, you say these collocation weights and the U weights. Once we add in different training schemes, we're looking at rolling in NTK weighting as well as like static, weights, hard weights in front of terms. We're rolling all that stuff in. So this interface may change just slightly, but you can roll all those things in just like this. It's the same number of training iterations, 2000 and 1000. The collocation points, the initial condition points, everything else is identical because I didn't rerun anything. And in this case, you go through, train. So in regards to your question about efficiency, so we saw here about 135 iterations per second. And so if we rerun that using the self-adaptive, then we'll you can see that we're going to get up to 100. So yeah, so we're getting pretty close to that by doing it. So in this case, it's a little faster. So these GPUs, since they're on Google servers, go back and forth. So usually it's not faster. It's slightly about 3 or so iterations per second slower. So it kind of varies. So here we got 140 versus whereas previously we had, what was it, 135. So in this case, it actually ran a little faster, but it's all subject to Google's server. So if you have a single GPU and you're running it at your house and you're not kind of subject to whatever is going on at Google server farm, it'll run just a little bit slower, about 3 or 4 iterations per second slower to do the self-adaptive. And of course, that varies heavily based on the number of collocation points and how complex your model is. So those are actually the 2 biggest parameters. In this case, we have 10,000 collocation points. And so, we're adding a reasonable amount of gradients to this problem. But even so, we're still running it on the Atom side pretty quick. The LBFGS actually doesn't train the self-adaptive weights. The self-adaptive weights are held static, and the LBFGS just trains the neural network weights based on whatever those self-adaptive weights were previously. So in this case, so we'll go through, so we said the same number of training iterations, right? 2000 and 1000. In this case, as we said, we'll get just a little bit better. In this case, 6.3 to the -3. So maybe a little over half of the error that we got with the same number of training iterations and the same, everything else kind of being held constant, just slightly better in this case. But in the Alan Kahn problem, which there is a notebook up, and if you're interested in going to see it, you can. I'm not going to run it for the sake of time, but in that case, that you can see that the training happened. There is a way of plotting the loss, or excuse me, the loss. There is a way of plotting that, as well as seeing the weight functions, the masks, like you were discussing. There's code built in for that too. But for the sake of kind of just giving a get off the ground style example, we'll leave it there. All the other documentation is available on GitHub, and then we have a website up for a lot of the other, kind of, like I said, I get a hacking section where you want to do custom neural network architectures. You can just overwrite it using a Keras network and roll that in. There's a few other things as well on here. You can kind of roll through and read up what the different capabilities are. But because it's built on top of Keras, it offers pretty much all the things that Keras neural networks have out of the box. So it's very useful in the sense of being able to do transfer learning or being able to define custom neural network architectures, changing the optimizers around. All of that stuff is built into this because it's built on top of Keras. And so, Dr. Braga-Neto, I don't know if there's something you wanted to mention that I forgot, because I went through that pretty quick.
I think you did a great job. I think this is a work in progress. Everything here is a work in progress. But, I think I should mention that people are already using this, right? You already have some stars already on GitHub.
Absolutely, yeah. So, and then the notebooks I was just going to show real quick. We have a few up right now, and we're building more of these out of the community as we get different users and get different user cases. We had heat conduction, or we were showing the reservoir. We're putting these up. So we have a few.
So on the Scientific Machine Learning Lab website, there is a link to the video of the class that Levi gave. It's like a 2-hour video. There's a short introduction by Jiantal, and then there's a 2-hour video by Levi, and he goes through in a lot of detail. So it's on the Scientific Machine Learning website.
Yeah. And so with that, I'll open the floor. I saw the chat was going. There's a couple of questions there. I think.
Yeah, we have questions from the chat, but let me first see if Raj is there. I want you to meet Levi. I want you to meet Raj. Raj, can you turn on your video?
Yes, I can.
Well, to put you on the spot, Raj, tell quickly, very quickly, what your latest paper and what you are doing with multi-GPU.
So this is hello. This is Raj from Brown. I work with Professor Kanirakesh.
Hello.
The recent paper which we put out on arXiv, it's basically implementing the C-pin and X-pin on a multi-node system. And maximum GPU we exploited was like 128 of Argonne and over 16 nodes and 8 GPU on each node.
Okay.
And we used the MPI plus X model. X could be CPU or GPU, because I assume that you have used the TensorFlow mirror strategy.
Yes.
Yeah. So it has a when I was implementing, it has an issue of going over the multi-node system. So because it's more of a kind of a database model-based parallelism, the mirror strategy, than the database. But here we have everything incorporated, like the database, model-based, and the MPI plus X, like through for the fabric actually.
Yeah, is that for? Did you release a package on that? I didn't.
No, the paper is under review. Once it is up, and then we will push it out. So
so that's a difference between, for example, because NVIDIA SimNets NVIDIA is pretty good parallel, but it's data parallel.
Yes.
Yes.
What we have with domain decomposition, of course, Ulisses knows because probably he's a finite element guy. This is domain decomposition, so it's space-time. So we have the model parallel and data parallel, all and the hybrid and everything. And so on 128 GPUs across 16 nodes, he gets 128 weak scaling speed up.
Yes.
On the new processors at Argonne, they have the Ampere.
The Ampere, yeah. Yes. So we have the Ampere architecture. They just kind of did a ribbon cutting at Texas A&M on our new. We have a new super HPRC for A100s as well. So that was what we were going to be looking at next.
So the reason I wanted to introduce you to Raj, because when you are free to travel, we would like to invite you to spend some time with Raj hacking around for a little while, okay?
Yeah, I would love to do that.
And I will be there to feed you with good food. But
hey, I love it. Yeah, so I've seen recent papers, and I don't know if it was your paper, but I did see an X-pin implementation that was based on MPI. And
yeah, that was Raj's. That was Raj's. Yeah, but he has improved it. He has improved it since then because he went to a Argonne lab, but there were some questions from the Apostolos. Do you want to continue your chat discussion with Ulisses?
Hi. Yeah. So this is Apostolos. Yeah, I work with George as well. Yeah. Actually, I just I told what I wanted to say to the professor. I shared the paper with this adaptive loss function, where they also have the same problem with monotonicity. So, and they use the corresponding probability density function. It's not super easy to normalize. You have to normalize it in each iteration. And for you that you have so many weights, I'm not sure if it's going to be easy, but at least it's something to look at.
Yeah, so you can tie the weights, right? I mean, like, these weights can be tied. Like, exactly. As any network parameter, but so let's say you have convolutional weights. But you can tie these weights to reduce. Even though, like I said, the computational effort is not really big as is now. But I'll definitely look at the paper, Apostolo, and thank you very much. I was not aware of it, so I'll look at it.
The other thing too on that, as far as computational efficiency is concerned, is when you start to get into a big domain, a really big domain, is like Dr. Braga-Neto was saying, tying weights. So you have like a partition of weights. Instead of each one being individual, you have a bank where you would, say, hey, all of these weights, and you would aggregate that gradient to train it for maybe 100 or tied into one box, if you will, in a three-dimensional space. You would aggregate all those gradients at once. So there's ways of overcoming some of those computational issues, and that was what we were going to be looking at for the self-adaptive for large domains, really large domains.
Let me add here that Apostolos' work, his postdoc, is to actually meta-learn the loss function. You don't assume MSC, you don't assume L1. Baron's paper parameterizes the loss function so you can get all these forms by parameters. But actually, Apostles went one step further. So he has a neural network that will learn what is the appropriate loss function for your problem. So it's learning the loss function. So it's
similar. It's actually a similar kind of thing.
It is similar. You sort of parameterize, you put the function, then you learn the function and so on. So it's some sense similar, but here he is doing that for the entire loss, right? So for the
and we also meta learn the loss function weights, for the loss terms that you were talking about in the
similar. He's learning also that, but he's also learning the norm. It's not the L2 norm. It's basically the functional space in which you minimize.
Oh.
So it is
very interesting.
But
this could overcome some of the training problems. Yes.
I want people to have a chance to ask questions, because I know that lots of people in our group are interested in this type of implementation. Sure. And so maybe anybody has questions?
Can I ask a quick question? This is Yeonjong from Brown.
Hey, Yeonjong.
Yeah, thank you for a very nice stuff. Very interesting, actually. But I have a couple of questions. One is is there any particular G function you guys recommend for the training pin?
A lot of our successful experiments have revolved around just a very simple x squared, quadratic G function. This is very effective.
X is clear. I see.
Yes, and that gives you it's a very simple function. It gives you all the properties that you want, monotonically increasing, differentiable everywhere. And so we did implement a lot of the sigmoidal masks we showed and the other things. We did implement those, but the most effective was by far the quadratic.
Wow, that's interesting.
Also, the weights cannot grow forever, so it's quadratic with a bound, with an upper bound.
Exactly.
But but it grows very fast. I think that's what helps, is that it really goes fast.
Right.
Then you guys put some upper bound so that the weight cannot grow a certain level. Is that
well? So we haven't trained on a horizon that's actually hit that cap. So usually we've only trained to maybe 40,000 or so iterations at most, and so typically, just because we don't let it go long enough to hit a numerical stability problem, now the other thing about if you use maybe a fourth order, you do x to the fourth or lambda to the fourth, is you'll run into numerical stability issues a lot quicker. So you'll end up, the training will start to fail because of numerical problems. You just, the gradients are huge, the terms are big, they can't add a big to a small, and numerical stability kind of starts to take over, and it's saying, no, it can't do it. So the x squared is a really good balance between accuracy as well as numerical stability in the training.
I see. Then you guys initialized your weight to 1, starting from 1, and
so the initial weighting is a hyperparameter that's been an open topic of conversation. A lot of the results that you saw were initialized to a random uniform distribution of 0 to 100 on the initial weights, and then 0 to 1 on the residuals. We've found kind of empirically to be a pretty effective means of training, but that's a hyperparameter that you can kind of select, and essentially you just multiply the initial values by some scalar, be it 100, 50, whatever it may be. Now, if you start it from 0 to 1, let's say random normal 0 to 1, if you start it from there, it will train, and you just got to let it train for a little longer. What we found is the way to get the results the fastest is to actually initialize those a little higher on the initial condition. The residual is kind of fun on 0 to 1, and that's specific for Alan Kahn though. Each problem is kind of has its own set of parameters. So yeah.
I see. That's interesting. And the last one maybe for the other people, but when you train ADAM after you apply LBFGS, do you also train the lambdas in the LBFGS?
So I have done that. It didn't prove to be very useful, and it slowed things down pretty tremendously. So we found it to be just it's just better to train all of the weights via ADAM and then hold them constant and let the LBFGS work on that loss function with those weights held constant.
I see.
So for a lot of the results, pretty much all the results you saw here, that was the training strategy. Was to just train the self-adaptive weights using ADAM, hold them constant, and then continue to train by LBFGS. Yeah.
I see. That makes sense. Okay, thank you so much.
Sure. Thank you for the question.
Good question. Yeah.
Any other questions?
Yeah, question as a follow-up to what Shin asked. So Ulysses and Levi, that's a good and great talk. Please, I want to ask, in the future, if this becomes standardized, will it open a new research area to learn the G?
It could, you know, I mean, there's all sorts of questions, and I don't know if Dr. Braga-Neto kind of just jumped into there, but you know, we've talked a lot about how do we generate, what is that G function? What is the best one? And it could be something that you learn, you know.
In penalty methods for optimization, they also have a soft spot for quadratic. Okay. I mean, it seems, yeah, so it is true. A quadratic works because it's like Levi said, I mean, it doesn't blow up too fast, but it also does not go too slow. It's a kind of a balance there. But yeah, I mean, so far as your question about I mean, we want people to try this and notice that we can try this with anything. We can try this with X pins, we can try this with C pins, we can try, I mean, it's completely agnostic to the particular pins that you, as long as you have a loss-based, you know, pin, you can stick those weights in, right? Okay. And you can train them together with the network weights.
The other thing too to that question is, if you're interested in trying your own functions, that support to define your own G function is built into TensorDiffEq. So you're more than welcome to, if you're interested in trying to find a better function, that's something that it supports right now. You can go in and you can roll that in, and it's in the documentation. And if you're interested, send me an email and I'll help you out with trying.
All right, thank you.
Yeah.
Okay.
Any more questions?
Hi, this is Ming Lang. I work with Professor Karnidakis. Very nice talk. I really enjoy it. But I have a very quick technical question. So could you explain, maybe I missed a lot of things, but could you explain again, like what is your base pins, especially for the 1D Alenkine equations? I'm not sure like why like the base pins have 90% error for solving the Alenkine equation. I've solved that before, so I didn't see that error, but so that's...
yeah, so let me take this one, Levi. So the one that we used is the one in the, you know, Raisi Perdikaris, you know, George paper. And we did that, so it's the standard one. It's not a discrete pin that is also on the in the same paper. The discrete pin solves the Alenkine. You know, but we didn't implement that one. We implemented the standard one, the continuous pin from that paper.
Right.
Oh, I see.
Yeah. So the continuous pin was the one, and then we decided, Dr. Braga-Neto mentioned White and Zhao, and they mentioned a similar problem and some ways which we discussed of how they overcame it too. So that kind of led us into where we're at.
But you know, Minlang, maybe weights 1-1, no adaptive activation functions, none of that. It's just the 4-year-old technology.
That's right. This is kind of unfair comparison, but
it's typical. No, you're not the first one. For the last 30 years.
But no, I mean, what I mean is, but you know, the good thing about this, George, is that you can apply this to any pin algorithm.
Yeah, no, the method is excellent, and the idea is excellent and very effective and simple. That's the idea, simple. So
thank you.
We appreciate that. It's that, as I said, there's many ways to go to Rome.
Yeah, and so you mentioned the adaptive activations is something that I was actually looking at implementing as well to see how it compares. So you know, we kind of took the baseline pin, we added this thing to it, and now we're, you know, we've been comparing it to, I guess, just by
because we have theory. We have theory. Our theorem says that you're not going to have, if you have adaptive activation functions, global or local or layer-wise, or especially now with the Rowdy, what we call Rowdy, Ameya, the postdoc, who wrote this, he took the shot today, the second dose, so he's not here, but the Rowdy activation function also allows you to put noise. That's why it's called Rowdy, right? Mm-hmm. So not only you have the slope adaptive, which is learned exactly the way you are doing, but also we have trainable parameters for the type of noise, the sinusoids that you put at the ends, -1 to 1. So then our theorem says that if you do that, you're never going to hit bad minima. It doesn't tell you that you will get a global minimum, but you will never get bad minimum. So we have theory, not the.
This is in the recent paper, right?
Yeah, but if you look, we have 3 papers published, and this is I think the 3rd one. The other ones are published now. The next one, this one on the archive, the Kronecker neural network, basically shows theoretically that the loss with the Rowdy functions is actually less than anything else. So not only we do that for pins, but one of our collaborators, Kenji, I don't know if he's listening, he's at Harvard now, he did this comparison with CIFAR-10, SWEN, all the NIST, all the commercial benchmarks. And using this activation function, not only during the training, we beat everyone, state of the art, but also it generalizes for testing cases, which we didn't have that before. For testing cases, much better. Also, it makes, if you have the high frequency, we have a Helmholtz equation with very high frequency.
Right.
Now the like you said, I don't think the weights would work here because it's very high frequency. So it's another issue, the spectral bias. The spectral bias, we solve it with frequency sine of 200 pi x. Okay. The other pins or the other activation functions, adaptive activation functions we tried before, cannot do that. You have to put the features like instead of x, you put sine x and so on in the as inputs. But that's messy. Here so it's actually for Levi's code. It will be easy to implement that in a couple of lines, which is basically your philosophy. Let the data dictate when will these neurons fire and when not.
Yeah,
exactly. And how much. And the interesting thing is to actually, just like you guys have the weights, the mask, this map that is developing, and then you show one snapshot, but it's actually developing, right? We also observe how these activation functions increase. So you start with a hyperbolic tangent, and eventually you see wiggles at the ends of this hyperbolic. So it's developing to pick up features.
Interesting.
So your philosophy, Ulysses, that's why they call you Ulisses. You are very inventive. So
it's a Greek name. It's a Greek name, you know that. Right?
It's all in the name. Is actually to let the data drive this. Don't make decisions. Of course, you need some help with the G, but that's
make
fine.
a small number of decisions. Yes.
Yeah, that's fine.
Yeah, exactly.
Any other question? Because we have one more talk, and I want Enrui to get back to that. Any other questions from the crowd? You had 50 people around the world, pin fans, listening to you guys.
Well, that's great. Yeah.
I appreciate the opportunity to
yeah, very much so. Yes, I appreciate the invitation, and it was a great conversation. I learned a lot. Thank you.
Jen Zhang, are you there?
Yeah.
So Jen is doing some drones, and he has these Hamiltonian systems, the SimpNets, and he has many drones going around. So he can have 100 drones. Nobody can solve that problem. His problem is that sometimes the drones go through the house. so he needs to put a hardware constraint with the right weights, and I think he will solve it this way with your methods.
That would be great.
Yeah. So anyway, thank you very much. Maybe Enrui, you can start the second session, and we'll be in touch, Ulysses and Levi.
We'll be in touch. Thank you.
Thank you. Thanks for the opportunity.
Thank you, Levi, and thank you, Professor Ulisses, for your great talk. So now let's go to our second talk. And our second speaker is Zongren Zhou from our Crunch group, and he will give a paper review about the paper with the title MorphNet, a fast and simple resource-constrained structured learning of deep networks. So let's welcome Zongren for his presentation.
Okay. Hello, everyone. Can you hear me?
Yeah, we can hear you.
Okay, great. So today I'm going to talk about a paper. The title of the paper is MorphNet, fast and simple resource-constrained structured learning of deep networks. So it's about neural architecture or neural structured learning method with a certain constraint on the computational resource. So, okay, the highlights of the paper are, first, it is, like I mentioned, it is a neural architecture learning method. Second is, this method is much faster than most the other neural architecture search algorithms. And third one is performance improved while the constraint, the computational constraint is met. So the assumption is we have limited computational resource so that we cannot allow a very huge network, or we cannot allow very large flops, like floating point operations per inference. So yeah, so that's assumption for this algorithm to work. So we first take a look at the high level structure of the algorithm, so we can go into details step by step. So the question is, what does MorphNet do? So it's like I said, it's a neural architecture learning method, and it learns the architecture by iteratively shrinking and expanding the network's width. So I think we have several talks in the Crunch seminars about the neural architecture search in the past 2 years, and there are three main aspects or three key points about the neural architecture search. One is search space, the second is search strategy, and the third is like how do we evaluate architecture. For example, when we're giving two neural architectures, how do we tell which one is better? So here, for MorphNet, for this algorithm, the search space is just a network width. So operations like convolution pooling and fully connected operation, those are fixed, and the total number of layers of the neural network is also fixed. So the only thing that changes is the width of the network, the number of neurons on each layer. So, and yes, like I said, this MorphNet learns neural architecture by iteratively shrinking and expanding network width, while the resource, while satisfying the resource-related constraints. For example, the size of network and the number of parameters, the number of total parameters of the network, or the flops per inference. So here's the algorithm. So the first step, there are the three main steps of the algorithm. The first step is we train a network to convergence and find the theta star. Here, theta is the parameters of the neural network. The L is the loss function. The G is a regularizer of the parameters of theta of the parameter of the network. So the first step is, of course, we train the network to convergence, and we have the theta star. The second step is we find a new, we find a new width. Here, O prime sub 1 to capital M. Capital M is the number of layers in the network, and the O prime, the capital O prime, or here the O naught is the list of width of the neural network. Like it records this. Yeah. So the first element of the O prime is the number of neurons on the first layer, and the second element of the O prime is the number of the neurons in the second layer. So it's just a list of the width, list of neurons, number of neurons on each layer. And the second step is we find a new width induced by this theta star. So giving a theta star, given the parameters of the trained parameter of the neural network, we somehow shrink the neural network and obtain a new width. Here, G, remember G of theta is a regularizer for the parameters. So it hopes to prune the whole network, meaning that we can eliminate some connections or some neurons from the neural network giving theta star. So for example, like I think I gave a talk on specification in deep learning a few weeks ago, and there's some pruning methods that prunes some connections in the neural network based on the absolute value of the weights. So in this paper, the authors of this paper didn't prune the network in this way. They prune the network based on other criterion, but the idea behind this is we delete something, we did some neurons, or we did some connections, we zero out some weight based on some criteria. And so the second step is we shrink the network. So we eliminate some unimportant things from network and we keep the important things. And the third step is we further expand the neural network. So after the second step, we have a shrunk width, we have a shrunk network. And the third step is we find here the omega is a scalar. So it's a multiplier, uniform multiplier for every layers. Here, this operation, omega dot product O prime is just, we multiply each, the number of layers on each, I'm sorry, the number of neurons on each layer by omega. So in this way, if omega is greater than 1, it's a expansion. If omega is smaller than 1, it's a further shrinking. So it's very simple operation, and we just multiply each, like we just multiply the number of neurons on each layer by omega, and we do this for every layer. And here, this F is a computational constraint. It's a constraint for computational resource. For example, like this F, giving a list of layers, we can surely compute the total number of parameters. So if we put a constraint on the side of the model, this F is just giving a list of the number of neurons it outputs the total number of parameters. In this paper, they propose 2 constraints. One is the constraint on the model size. The other is the constraint on the flops per inference, meaning that like the number of floating point operations performed in a single forward propagation. So if we, like after we train the network, we have the well-trained network, and we need to use that to do inference, to do predictions, so which may require many times of calling this neural network. So in this way, the flops, the operations per inference matters. So this is the second constraint that this paper used for this MorphNet algorithm. And after the third step, in the third step, we need to find the largest omega. So we wish to we prune the network. After we prune the network, the expressive power of the neural network in general decreases. So we need to enlarge it. We need to further expand it. Well, the resource, the computational resource is satisfying the constraints. So after that, after expanding, so in general, for most experiments the author's paper did, omega is greater than 1. So it's expanding procedure. And the fourth step is, yes, it's an iteration. So we do step 1 again, and then we do step 1, 2, 3 again and again and again to obtain the final width or the final structure of the neural network while the constraints are met. So the first question, so there are certain designs we need to make. First one is what is the G, what is the regularizer? And the second one is what is this constraint F? And the third one is giving a parameters of the weights, giving a theta star, how do we construct a new structure? So first, what are the constraints? Like I said, the paper used 2 constraints. One is I'm sorry, I made something wrong. So the question should be what is the constraint? It's not what is regularizer. So yeah, there are 2 constraints. One is constraint on the model size, and the second one is constraint on the flops. So here, this F for the L layer, here C is capital C is a function, and capital I sub L and capital O sub, they are input and output dimensions of the layer L. And since in this paper they considered the output of this paper is considered convolutional neural network, and but also it also applies to fully connected neural network, since the fully connected operation is just it's a special case of convolution. We have just a huge convolutional, a huge filter for the entire input. So for example, if the constraint is the flows per inference, then we have here F, G are the shape of the filter, and Y, Z are the size of the output image, since they're considering CNN convolutional neural network, where they use the input and output the input and output of the convolutional layers are both images or matrices. So here the omega or Wx, they are shape of the input image or input matrix, and YZ are the shape of the output matrix. And if the constraint is on the model size, then since remember the weights are in the filter, so the number of weights has nothing to do with input shape or output shape. It only depends on the size of the filter, since filter is our weights. So if we consider this constraint on model size, then they see these parameters, the number of parameters is just F times G, which F and G are shape of the filters. So those are examples of constraint function. So, and here they use to further, since here, this function certainly evaluates the computational complexity of the neural network, but it has nothing to do with theta, with the parameters of the neural network. Since remember, we need to find a new structure based on the theta star, based on the trained parameters with the neural network. So we have to transfer this function, this computational complexity function, to some function, to a function that depends on the theta, the parameters. So here A and B are indicator function, which equals, they are indicator function for the at input or j output of layer L, like demonstrate whether the neuron is alive. So the interesting point of this paper, of this algorithm is, unlike other pruning method, they don't prune the network based on the weights. A lot of pruning methods prune the network based on the absolute value of the weights. They assume that when the absolute value of weight is smaller than some certain threshold, then this weight is unimportant. This weight should be zeroed out. And so remember, in neural network, a weight represents a connection between two neurons in consecutive layers. So by zeroing out a weight, they essentially delete a connection. But here in this paper, they don't eliminate weights. They don't delete connection, because I think in the previous talk, when I talked about specification deep learning, even if we zero out, we delete some connection, so the weight of that connection becomes zero. The computational complexity, I think Yang Liu asked this question. The computational complexity remains the same, since it's not a sparse matrix vector multiplication. We have we have a matrix multiplication or matrix vector multiplication. If one element or several elements become zero, still we need the number of parameters, the number of operations is the same, since we still do matrix vector or matrix multiplication. So it doesn't decrease, the computational complexity doesn't decrease when we simply eliminate connections. So in this paper, they prune the network by eliminating neurons on each layer. So they have a criterion deciding which neuron on each layer is not important. So they zero out the neuron, and instantly the weights or the for fully connected layer, the size of the number of the parameters decreases instantly after when we delete neurons from layers. So here A and B are indicator function for each layer. So for each neuron of layer L, if the neuron is live, the neuron is important, then it's just 1. If the neuron is not important, if the neuron is deleted, then this indicator function is 0. So, and the total computational complexity is the summation over the entire layers, the entire neural network. Okay, so, but here again, so we want, remember the first step, we need we train, the algorithm trains the network convergence. So with the regularization, this regularization has to be a function of the parameters. So this function, this f, which is the computational complexity function, doesn't take theta as an input, doesn't take the parameters of neural network as input. So to further modify that, the authors proposed a regularizer function G. And so here, and B and A are still indicator functions for neurons. Here for neurons. And OL means is output of the alpha layer. IL is the input of the alpha layer. So here, so they use this gamma, this as a criterion to prune the network, and also use this. So that this gamma is the parameters. So they use this for the regularization. So what is this gamma? So this gamma, remember, is element-wise, is neural-wise. So we have each neuron corresponds 1 gamma, a unique gamma. And this gamma is just a scale parameter in batch normalization. So the author assumed that when we deal with computer vision problems, when we deal with images, we use mini batch to do the training. And so batch normalization, we always use batch normalization for mini batch training. And so and you can see that for Y at first, this I means each neuron. So they use, after the normalization, they use gamma and beta. Gamma is the scaling parameter, and beta is a shifting parameter. They use gamma and beta to recover the output of the layer. So here the gamma, the MorphNet algorithm uses this gamma as a criterion for pruning, and they uses this gamma for regularization. And here are some results. So this is a figure, it's a histogram of gamma, this criterion gamma, or absolute value for just, okay, I forgot to mention one thing. So to start this algorithm, we need to design like a seed neural network. We need to start with a neural network designed by hand, and then we proceed. We further improve the performance of further shrinking and expanding. We do this shrinking expanding procedure on this seed neural network. So so this figure is a histogram of gamma for one trial, for the experiments on this FreSNet. And the constraint is on float, is on operations per reference, per inference, and you can see that from the histogram, there's a very significant gap between zero gammas and gammas with larger absolute value. So so remember in the second step of the algorithm, the here gamma in batch normalization, gamma is a parameters. So gamma and beta become parameters of the network, become the trainable parameters, trainable variables of the neural network. So yeah, and so after they train so gamma is part of the theta, part of the parameters of the neural network. After they train the network convergence, for each neuron we have a gamma, and the method just put a threshold on the gamma and decide which neurons to be deleted. So I think they set a threshold. They set a 0.01 threshold for all neurons. And here is a table, and so accuracy. So this is iteration. So okay, there's another advantage about this method. So the algorithm finds the better or a good neural architecture by iteratively expanding, shrinking, and expanding the previous one. So, but in the iteration the number of iterations doesn't have to be very large. Here in the experiments, they just do like 1 or 2 iterations. So after those two iterations, you can see the accuracy improves a little bit, while since they put a constraint on the flow on flow per inference, the total computational complexity doesn't change much. However, there's a very interesting thing that the computational complexity is very similar, while the number of ways is not. So a lot of neural architecture search algorithms, when they do the comparison with Heim design architecture, they always claim that they have the same amount of weights or the same amount of parameters, or very similar amount of parameters in their automated neural architecture. But here's the point: even if we have two neural networks, they have different architectures. Their weights are the number of weights, the number of parameters are the same, but the computational time can be very different, since like different connections or different active functions. There are many factors influencing the training time or the inference time. So here, after 2 iterations, the weights, the number of parameters, the total number of parameters increases, but the computational complexity remains very similar. So that is a good thing. Oh, there's another result. It's another table for the result. Still, they are constraining the flow per inference, and so we can see that their computational complexity, the time is very similar for training or for inference are very similar, but they have like the accuracy improves a little bit. And okay, so this is about this paper. So here are some thoughts and comments. So there are many advantages of the algorithm. So one highlight is the performance improved by finding the better neural architectures, while the computational complexity remains very similar. So they claim they have improved performance at no cost. So this cost regards flops per inference or the cycle model. So the second advantage is that the algorithm is very computationally friendly compared to other neural active search algorithms, since they integratively expanding and shrinking the network, the previous neural network. But since the total number of iterations required is not that high, it's just 2 or 3, so it's very computational friendly. And third is because of the second advantage, it is highly scalable to a large network. So even if we want to find giving a very large seed architecture, we can also this algorithm can also be applied, and the training or the finding procedure is relatively fast. And four is I think that's just my comment, is I think it's more friendly to physically informed neural network, since when we use pins, when we use neural network for PDEs, we most of the time we use fully connected layers. Oh no, fully connected neural network. For most neural architecture search algorithms recently, they search for they many search for convolutional neural networks. So they search for convolutional operation, search for pooling operation, or downsampling, upsampling operation, which those are not necessary in pins, in physically informed, in fully connected neural networks. So this algorithm, this MorphNet, search for weight. So which is it can be utilized to further to improve our work, to improve physics from neural networks. So remember, this is this is one slide from Lulu's talk on automated machine learning in last 2 years, like in 2019. So like I said, there are three aspects, key aspects about the neural search. First is search space, the second is search strategy, and third is the performance estimation strategy, i.e. how do we evaluate the performance of one structure. So for most, for a lot of neural search algorithms, the strategy, the performance estimation strategy is very poor. So they just giving a structure like for example, a sequence of a list of layers. They estimate the performance by training the neural network induced by this architecture to convergence. So this process, this training process takes a lot of time, and they need for some algorithm, they need to do this again and again and again. They need to do many more iterations. So which implies that, which certainly if we don't have that amount of time or that amount of the computational power, it's not doable. And so like I said, so for neural active search with reinforcement learning, they use reinforcement they use this. Okay, so they use this, the search strategy is reinforcement learning, and the problem is with when they evaluate they need rewards to train the reinforcement learning controller. So they need rewards to train the policy, but this is relatively quick to generate a policy, or in this case an architecture, but it's very slow to get the reward of the of this architecture, since we need to train this architecture to train the neural network induced by this architecture to convergence. And so another work about neural search is progressive neural search. So this method proposes a surrogate model for the evaluation. So basically the surrogate model is not a neural network. So the input of this neural network is the architecture of the architecture. Could be the list of layers, could be a sequence of the architect of the operations. So and the output of the surrogate model is the score, or the whether or not the accuracy or the error. So in this case, after several iterations of training, they don't have to train, giving a new architecture, they don't have to train to converge. They just feed this network to the surrogate model, and in a short time they will have the reward. So this is an improvement on the performance estimation strategy. So and for other works, for example, for efficient neural network search via parameter sharing or the DARTs, differentiable architecture they use, they're different from MorphNet. Instead of the width, they learn the connection and operations. So and the key points of those two methods are parameter sharing. So they don't have to, when evaluate structures, they don't have to train them to convergence. They can do it by, iteratively, like they can do this evaluation very quick, and parameters are sharing, some ways of the connections are sharing between different structure. So compared to those neural network search algorithms, this MorphNet has some advantages. I already mentioned that, but it also has some disadvantages. First, compared to those algorithm, the search space is very small. So in this paper, this MorphNet algorithm only search the width, and even and the width multiplier is uniform. It's the same for each layer. So the small search space accelerates the whole searching process. But what if the optimal or the good architecture is not in this search space? So that is a big question. So this is a disadvantage of the MorphNet. So it only searches the width. And the second one is the algorithm prunes the network by the scaling parameter, the gamma, from the batch normalization, and based on the assumption that the neurons with small absolute value scaling parameters are not important. So it seems to us that it is better than the assumption that connections with small absolute value, like weights with small absolute value, are not important. This assumption is considered weaker, or not weaker, but this is worse than this assumption. But however, this still it's not the case for especially for a regression problem. For example, if we have this, we will regress this function, and when x is around 100. So and for example, this is our gamma, and because this gamma is really small, so we zero out, we delete these neurons, so we no longer have sign of x anymore. But this doesn't matter much in classification problems, since for classification problems, we only need to find good boundary between classes. But for regression problem, it matters a lot, I think, because if we zero out the sign, x, sign of x, then we lose a lot of things. We lose oscillations. So assuming the assumption that the assumption this paper made on what the importance of neurons doesn't hold for all the cases. Okay, so this is basically it about this MorphNet, about this neural architecture. So this is not exactly neural architecture search, because the search space, I'd rather call it a neural architecture learning, since the search space is very small. So when we talk about searching, it should be a larger search space, so we can search connections, we can search active functions, we can even search the depth of the network, or the like operation of in the network. But in this case, you just search the width, and the search strategy is even simpler. It's searched it with shrinking and expanding the seed network, the previous network, and this expanding process is done by a uniform multiplier, weight multiplier. So I'd rather call it search neural architecture learning, or neural structure learning. And yeah, so any question about this MorphNet? Any question about the search strategy, or this search space, or this, like, any questions? No?
Oh, I have a question. Hello. these are true. I have a question. So there are many ways to increase the width or shrink the width of any neural network. For example, in pins, I know I use the automatic differentiation to increase the width of the neural network, but there's other ways to increase it. Or, I mean, you said I increase the performance, right? So my question is that you can perform any operations on the neural network, increase it and shrink it, or it's only a multiplier type of operation?
I'm sorry, I didn't catch that. So what is the question again?
Like, what operations can you perform to increase or decrease the size of the neural network width? Like, what are the possible operations that you can perform?
I'm sorry, you're talking about expanding and shrinking the neural network?
Yes.
So what is the question? I'm sorry, this just there was.
Oh yeah, so you have a function which has like this W, this omega, this W, sorry, so this W has a multiplier times the O prime, which is the step after in the neural network when you expand or shrink it. So what operations can you perform in order to increase the neural network or decrease it, and what are the possible operations that you can perform, and what are the advantages, disadvantages of different operations being applied to the neural network width?
They don't have many operations. So just the shrinking and expanding are done on neurons, on the number of neurons on each layer.
So the number of neurons, okay. So okay. Yeah, so it could be any operation to decrease or increase the number of neurons in the layer. Thank you.
No problem. Any other question?
So, I mean, this is very interesting work. Do you have an archived paper on this?
This is my work. It's just paper put on archive. You want so okay? You can search that archive. It's a work done, I think, in 2017.
Okay, thank you.
Sure.
That's very interesting. It's something that we are also interested in. Yes.
Is there any other questions? Yeah, if not, let's thank Zongren for giving this talk. And just now, Professor Braga-Neto, just now I have put the title of the second presentation, the paper, in the chat box, and maybe you can copy that, and it should be easily searchable from the Google Scholar or something like that. And
thank you very much. Yes.
And yeah, thank you everyone for attending this week's Crunch seminar, and wish everyone have a good weekend, and see you next week.
Thank you.
Bye.